Well, thank you everybody for joining us again on our COVID-19 relief effort brought to you by Johnstone Supply and FlexTrain, a flexible training opportunity. So today we're going to be talking about basic electricity. So we spent a couple days going over duct design and airflow, and we're going to move now into one of our CEU classes called basic electricity. And remember, it's just going to be a portion of that. It's not going to be the entire continuing education program. It's just going to get us into the highlights and get us into understanding the functionality of different components of our HVAC industry. And on Thursday, for those of you that have never participated in our FlexTrain Thursday class, and we do have a separate registration, because the one that you have for this is going to get you Monday, Tuesday, Wednesday, and Friday. On Thursday, it is a separate registration, and that is on our Johnstone Solutions University calendar. And this Thursday, I've actually changed what we were going to be talking about, ECM, evaporator blower motors, but we did that a few weeks ago. So we're going to talk about manometers. Since we were doing quite a bit of airflow and duct design, we're going to dive into manometers and talk about those quite a bit. So today and for Friday, we are going to be doing basic electricity. And Greg, you want to get us wrapped up on this? And if we want to, let's reintroduce ourselves just a little bit. My name is Clifton Beck. I'm a technical solutions manager for Johnstone Supply. I cover primarily the central Indiana market, but here at the Grimmie Group, we have 9 locations throughout Indiana, Ohio, Kentucky, and West Virginia. I've been in the field, spent about 21 years out in the field doing residential, industrial, and commercial HVAC, refrigeration, and electrical, and came to Johnstone Supply about 2.5 years ago. So 2.25, I guess it's been. So very glad to be here, and just love being a part of this program. Paul?
Yeah, my name is Paul Grimm. I am the Tech Support and Training Manager for Johnstone Supply in the Central Illinois Group. I've been 24-ish probably years of technical diagnostic background. Started in a little bit in electronics, then 12 years in the automotive industry as a technician, and then 11 years in the field as a service tech for HVAC. Been with Johnstone about 1.5-ish, somewhere around in there.
Nice. Thank you, Paul.
Greg Millsap's about 35 years in the field. I started when I was 3. Service tech, service manager. Now I'm on the training side of it. I enjoy it. I enjoy going into high schools and talking to the kids about skilled trades. I think something we sorely miss in this country is teaching kids how to actually do something. But I don't want to start preaching. So, Jesse.
Hey, good morning. My name is Jesse Huber. I am with Johnstone Supply Grimmie Group as well. I am also located in Indianapolis, and I have been with Johnstone for almost 11 years now.
Jesse is he's a little bashful on all of his background. He is actually a phenomenal subject matter expert. We have recently recruited him into the technical support field because of his vast knowledge of equipment and products. So thank you, Jesse, for joining us.
Mm-hmm.
All right, guys, so we're going to dive into basic electricity. We're going to cover some basic objectives. We want to talk about identifying parts of an atom. We're going to use Ohm's law to explain some of the mathematical relationships of voltage, current, resistance. We're also going to go through and contrast some of the properties and applications of static electricity, a little bit about DC and a little bit about AC. And then at the end, we are going to have we're going to have a quiz again. I have to say, I kind of threw a little bit of a curveball on you guys yesterday. Not a single person got 100%, is because on the first question, I actually did a little bit of geometry and moved our calculations back. So there were 2 different answers that were correct on A. So we had 2 more people get what I will consider perfect scores. They did not get the little curveball that I threw in there. So I've had 3. Rhett Harkins, you won another prize. Rhett won one from Monday. Jason Scherer and Cameron Kelly. So Jason and Cameron, I don't know that I see you on here, but I got a pretty good list of people. Get with me and let me know what branch you want your little multi-tool picked up at. All right, so let's dive into basic electricity. So the actual design of our electrical circuit is going to be either a series circuit, a parallel circuit, or a combination series parallel circuit. And so as we add resistance into our circuit, it's going to change the way that we drop voltage across that circuit. So when we apply voltage onto our control, depending on how we maneuver our resistive load inside of that circuit is going to change the flow of our electrons, and it's going to change the amount of resistance or the voltage drop across based on that resistance. So either we're going to flow across a path and a parallel path, and we're going to stop at each resistive point, or we're going to have a cumulative resistance when we're in a series circuit, and we're going to go from one resistance directly into the next resistance, and we're going to lose. We're going to basically create an independent resistance at each point. So if we think about a gate, one of the things we always want to talk about when we're talking about electricity is how electricity flows. And we're going to get to that here in the next couple of slides. And we don't want to spend a lot of time just because this is just an objective to know that we are going to discuss, what the effects of series parallel and series parallel circuits are based on the flow of electrons, because that really is the thing that we are going to discuss in this class, is we're going to understand the fundamentals of electrons and how they flow, because it's very easy to understand how electricity flows if you use it in correlation to other mechanical processes that we already know. If we think about the flow of water through a plumbing pipe, it's a pretty simple process, right? We understand that we are taking a molecular compound and we're moving it through a channel, and we're using a resistive surface on it to maintain it in a conductive flow, right? That's all we're doing with electricity. Electricity is a flow of electrons. If we talk about electrons, electrons are a composition of our atoms. So atoms are made out of protons, neutrons, and electrons. And that is one of those fundamentals, like Greg said with the Ohm's law. We learn about a lot of this stuff in class, but we didn't put it into actual practicality. When we put it into practicality, we start understanding, if we look at it as it's right in front of us, let's understand this, let's see it and compare it to something that we already know. So when I talk about the flow of electricity in the use of electrons in parallel circuits, series circuits, and combination parallel series circuits, think of it as this. If we think of a molecule of water flowing through a conductor that has an insulative property to it to maintain that flow, think of electricity in the exact same philosophy. Think of electricity as electrons flowing through a conductor that has an insulative property to it, because it really isn't that what a wire is? It's a conductor that is insulated by some type of insulating material, and our electrons are flowing through those conductors. Where we get misdirected and where we lose our focus on correlating that with water is we think of water molecules as flowing continuously. Water molecules are moving, electrons are moving, and they're moving through a conductor that is insulated. So we need to think about that process, because as we start talking about electrical circuits, and hopefully we'll have enough time, we'll dive into some of the electrical circuits and understanding what resistance looks like. If we take those electrons, when we hit a resistive structure, if we hit a gate, that's what a resistor is. A resistor is a place where our flow of electrons have been reduced. If we think about that in water, that could be as simple as going from a 60 psi of pressure, which our voltage is pressure. If we look at it from those correlations, voltage is the amount of pressure. If we're talking about water, it's psi. If we're talking about electricity, it's in voltage. If we take a certain amount of voltage and we are bringing it through a conductor and we reduce its volumetric flow down, if we go from a 3-inch pipe in water down to a 1-inch pipe in water, we still have our same psi, right? We just have less of its flow, less of its atoms of water moving. Electricity is the exact same thing. If I go from a large conductor down into a small conductor, I can still maintain my voltage, I can still maintain my pressure, but because I have resisted my flow of electrons, I have changed how I have applied my voltage. And if I go through multiple resistives, I'm going to change my amount of pressure across those. And we'll get into that just a little bit more. So this is what I was talking about by electron flow. If we talk about those electrons that are moving around the nucleus of our atom, they actually move from particle to particle, and they do flow. The better the conductor, the easier that they flow. Sure. So every particle that we look at, every atom is going to have some type of a neutron and some amount of protons. And then surrounding it is our orbital electrons. And the amount of orbital electrons is what we're looking for. The amount of electrons that can be passed from one atom to another atom is what changes our actual conductivity, our electron flow. If we are going to use these to start plugging into numbers, if we want to compare our flow, if we look at the potential difference in atomic charges, and if we're looking at voltage, it's an amount of electrical pressure generated by our source. If we were comparing that to water, it would simply be the amount of force that we're using, our PSI. So 1 volt is equal to an EMF, electromagnetic force required to send 1 amp of current through a resistive ohm. So we're just simply talking about flow. Flow of electrons, we can actually measure at 1 amp is actually equal to 1 coulomb per second. So now we're going to talk about speed. So if we talk about an amp and we're talking about how fast an amp can move per 1 coulomb per second, if we're talking about water, aren't we really talking about gallons per hour, gallons per second? We're talking about the actual flow of our water through that conductor. With electricity, we're simply going to measure that as our amperage. So we can correlate all of our electrical flow versus a mechanical flow of water, hydraulic flows. We can use all that to be a comparative against different mechanical forces.
Can I give you a little perspective on that real quick?
You betcha.
That backup one, would you, Clifton? Because this is actually called a coulomb.
Yeah.
I think it's the actual pronunciation of that. And it's what it's intended is, and it's somewhat arbitrary number, by the way, is the amount of electrons passing a certain point in a conductor every second. So the actual atomic electron going through a point in a conductor every second. And that number down at the bottom there may seem like it's fictional. It's 6.24 times 10 to the 18th power.
Yes.
Does anybody know what that number is? You should give a big prize for the person that can name this number, because that's it.
There you go. All right.
So, Paul, you seem to be another mad scientist like our boy Beck. Does anybody know what that number is? It's 6240 followed by 15 zeros. So I've yet to everybody tell me what that number is, but that's a lot of electrons.
Jesse, there's one for you. Work on a million billion.
Yeah. I wanted to throw something in there.
There you go. Do you want to run with any more of this, Greg?
No, you go ahead. I like the pressure part you did in the actual class for the CEU, showing that water pressure is like voltage, and the current is the flow of water. So the more pressure you have, the more current flow you have.
Absolutely.
And I guess pressure being rated by the actual voltage of it. So go on. I got some stuff to add in here too, some jocularity.
Okay. All right. So if we look at our relation, go ahead, Paul.
You jump back one slide, just a practical application of that. The height of the water is what gives you your pressure down, right? That's why we have water towers. They store the water up high to give pressure to cities. So
don't go too deep into that, because we're actually going to dive into the mathematical calculations on Thursday for heights of water column versus pressure. So yeah, but absolutely it is. That's how we increase our pressure. We increase it by height, and there is a mathematical factor for that. And
oh, that's a great point.
Yeah, we're going to go over that on Thursday. All right, so if we look at about a relationship between voltage and current, so say we're going to work on a circuit and we're going to use a conductive load. So in any type of a circuit, we're going to have our supply voltage, we're going to have our conductors, and we're going to have a load. If we use, in this particular example, we're going to use, say this is probably a D-cell battery, which is, typically around a 1.5 volt load. If we put that into our circuit and we just make a completed circuit is just our length of conductors. We typically going to have some type of a switch on that load that is going to slow down or stop the flow of electrons through our circuit. If we increase, oh, thanks, Jesse. It is a quintillion, by the way. If we increase
come up with that.
the amount of capable flow of our electrons, we're going to increase the amount of pressure. If we look at batteries and generators, so we use a battery for a single purpose. A battery is a storage device for electrons. We use a generator to generate electrons, right? We're going to pull them out of the magnetic field, and we may dive into that in our other presentation here in a minute. And we're going to use a battery to store our electrons. We use a capacitor in the same way, but a capacitor is used to discharge those electrons very rapidly. So a capacitor is going to be a container that is going to store our electrons that we can release very quickly. So we're going to have one large open gate on our capacitor. It's going to let everything flood out in a hurry. So we're going to have an inrush of all of those stored electrons. In a battery, we are going to store those electrons, but we're going to store them on a very lengthy plate, and we're going to allow those to flow at a continuous rate, a solid amperage, a potential amperage. If we want to increase the flow of our electrons, we increase the capability of our pump, because essentially a battery is going to be a pump for our circuit. It is what is going to move our electrons. It's going to build up pressure. Remember, voltage is pressure. It's going to store those electrons so that it can maintain a particular pressure, and then it's going to move those electrons in that particular pressure. It's designed pressure, it's designed voltage. If we use those same principles and we just multiply our potential pressure, we can increase the actual voltage. So if I take two 1.5 volt batteries and I put them into a series circuit where I am pumping from one pump directly into the other pump, I'm going to increase my amount of pressure. If we're thinking about, fluid dynamics and hydraulics, if we take a pressure from one pump and we bring it into another pump, we're going to multiply and increase its pressure, right? Same thing with our batteries. If we have them in a series circuit, we're going to take our electrons, our amount of pressure that we have available, and we're going to take that pump and we're going to move it into a secondary pump, which is going to increase the pressure on our electrons. So if I take a series circuit of two 1.5 volt batteries, and I bring one 1.5 volt pump into the next 1.5 volt pump, my output pressure is going to be 3 volts. I have increased my pressure by moving through those two pumps. If I put them in a parallel circuit where they're next to each other, and my conductors on my negative side, my positive side are tied together, I am pumping the same amount of pressure. I have two separate pumps, but they're moving the same amount of pressure. So I only have the available pressure of 1.5 volts because both my pumps are moving next to each other. They're not pumping from one pump into the other. But I have now doubled my capacitance of it because I have two pumps moving at the same time. If I have two water pumps next to each other, each of those water pumps are capable of increasing to 10 gallons per hour. If I have both of those pumps running at the same time, my pressure is going to be the same. Whatever's coming in is going to be equal to what's coming out of each of those pumps. I just have twice as much volume, right? If I take two pumps and I put them in front of each other, I have one pump that is stepping the pressure up to the next pump, but I only have the capability of that single circuit. The same way in electricity. I can increase my voltage, but I'm going to have a lower current draw because of that. If I have my pumps in parallel, my batteries in parallel, I'm going to have twice as much capable pressure, but not the volume. So we have a direct correlation between voltage and amperage, depending on whether we're using that parallel or whether we're using that series circuit. Now, so we've talked about our batteries and our generators being our pumps. They're going to increase the amount of electrons that we have capable of flow. Well, we're also going to have loads, right? We're going to utilize those electrons for some purpose. If we have a resistive load, we're going to change the way the electrons flow through that path. If I have a simple resistor, all I am actually doing with that resistor is I am affecting the flow of my electrons. I'm choking the flow of those electrons, right? So if I look at the flow, when we go back to the correlation between our voltage and resistance and our amperage, 1 ohm equals the resistance that will allow 1 volt to conduct 1 amp. So we are changing the way our electrons flow through our circuit. And similarly, if I take one resistor of equal value in a parallel circuit, I'm going to be able to resist at about the same correlation, right? I can get my volume through there, but I'm just going to resist the way that I flow through the two of those. If I put them in a series circuit, I am now going to significantly reduce my flow of electrons because I'm going to reduce it at my first resistor. And as I move it into my second resistor, I'm going to reduce that output even lower. So if we think about that from an aspect of plumbing, if I have water flowing through a pipe and it stops at a type of resistance, say I go from a 3-inch pipe down to a 2-inch pipe, that is my resistive, right? Doesn't necessarily mean that my voltage is changing, but I'm definitely changing the way that I flow through that material. If I then, right after that 2-inch, drop from a 2-inch down to a 1-inch, I can still maintain my voltage flowing through there, but I'm going to lose some as I pass through there. I'm going to lose some of my electrons because I don't have quite the volume. I can still potentially maintain some pressure, but I'm going to lose my actual flow. And depending on whether we're using a parallel circuit or a series circuit is going to change how we flow those electrons through and how much pressure we lose in the process. Get another slide here. So there's our basic Ohm's law. There's the effects of Ohm's law, our E versus I versus R. All right, one way that we want to look at in the HVAC industry is to look at the resistive effect of electrical heat strips. So if we take an electrical heat strip and we know some common factors going to that, we can plug in and find our differential factors. So we got an electric furnace and we know that we have 241 volts being applied to that thing. And we take our amp meter. So we've taken our voltmeter, we put onto our electric heater. We've got 241 volts being applied to that heater. And we have now used that resistive element, because remember, that's all our electrical element is a resistor, right? I'm not using that as a resistive in a series circuit. That is now basically become my parallel circuit. That is my load on that resistor. So I'm going directly from my line through a conductor into my load. And because I have choked down the way that my electrons flow through that, my electrons are going to be restricted on the way that they flow through that, right? Because our electric heating element is still a conductor of electricity. It's just resisted, right? We're going to be going from a 10 gauge copper wire down to a small, typically steel or coated conductor. It's going to have a very significant amount of resistance across that wire because we have now choked it down. We went from a fairly large conductive wire to a semiconductive wire that is extremely long. You think about the distance of an electric heating element if we unwind that thing. That's a significant amount of resistance that our electrons are going to try to flow through. So we take that, we coil it down into a small area so that we collect the resistive heat that is being generated by our electrons that are being choked down through their conductor. And we can calculate exactly what the resistance is on that. So if we take 241 volts being applied to an electric heating element, and then I take my meter and I check the amount of current that is flowing through the conductors going to that heating load, and I've got 19.7 amps. I can simply plug those into my Ohm's law. I've got my volts and I got my amps, right? I can plug those in and I now have an exact resistive factor across that. simply by plugging those into our Ohm's law calculation. So very, very handy thing to have when we're talking about electrical
I think
conductivity.
it's important to know that, like, most of the time we use electricity, we use it through magnetism. This is resistive load, so it's a different kind of load. There's no inrush of current on a resistive load, but it's just like the eye on a stove, to put it in perspective. The eye on the stove is the exact same principle as a 5 kW heater. It's almost a dead short through a very high resistance factor that creates heat, and then we blow air across it in the case of electric furnace, and we put a pot on it to boil our spaghetti on the stove, but they're basically the same thing.
Absolutely. Greg, you don't continue running with any of this?
I got so much things going on in the background here, I'm afraid to. That's why I was off there for a minute.
Could you jump back to the Ohm's law thing too, just for the guys who maybe haven't seen that or are familiar, just the chart. So with this too, just think about it as a like a thumb diagram. If you have E, your voltage, that's what you would cover up with your thumb, and then it shows you that you need to multiply I times R. So the voltage is on top, your resistance and current is on the bottom. So if you, so in that first, on the upper right hand corner, you have your voltage. You would cover that up, and it's showing you that you need times your I times your R. The second one down, you have resistance. You need, or you're solving for resistance. I'm sorry, I'm saying that wrong. You're solving for resistance, so you're going to cover up the yellow there, and you would divide voltage by current. So it's a thumb exercise, basically.
Absolutely. Yeah, and I don't know if anyone's ever seen that before, because it is absolutely a very handy one. You can simply use that chart and cover it up. We have a service manager workbook that I've been putting together, and that's one of the things that I do is I actually take the Ohm's law charts and have it printed out on the book, so the guys have it handy, and it's actually finger size. You know, it's a little 4x6 binder, so you can simply plug it in. No, very good point. Okay, move on. Like I said, some of these we're going to have to actually skip through because we have so much of this that gets covered in our continuing education classes that we're probably not going to be able to get covered today. And a lot of the stuff we're just we're pulling in to have these exercises. If we talk about the difference between DC current and AC current, DC current electrons flow in one direction. When we were talking about electricity as an industrial electrical supply, we initially were looking at DC as the supply power for our world, and we end up switching over to AC. We currently use DC in our automotive industry and a lot of our electrical controls. DC only flows in that one direction, so our electrons are only flowing one path. If we're talking about AC, we're actually using a reverse generation, or we're talking about a sine wave, so that our generator is actually rotating on its magnetic field, and we'll go through that here in a minute actually. And so we are pulsating in a reference, so we're not just doing a direct DC generation, we're actually cycling, and we're going to pull that into part of our test here in a little bit. So if we talk about frequency, if we're talking about AC, if we're looking at a generator, so if we're rotating, if we're moving a rotor inside of a stator on a generator, our magnetic fields are actually reversing. So, you know, we're getting, if we're thinking on a positive and negative reference, we're actually reversing our polarity in a cycle. And so when we talk about hertz, when we talk about the hertz that we're using here in the United States, we focus on a 60 hertz cycle, and a lot of places around the world we talk about a 50 hertz cycle. What we're talking about when we say hertz is we're talking about 1 hertz is 1 cycle per second. So that is a cycle. It's a revolution of our actual generator. So it's a revolution of our rotor inside of our stator. Here in the United States, we actually function on 60 cycles. So we are actually doing a 60 cycle per second frequency. That's why if you ever look at a fluorescent light and you see our pulsations, we're actually looking at our pulsation of our generator frequencies are 60 cycles per second. All right, now if we talk about some of our different conductors, you know, when we're looking at water and we talk about conductors of water, we typically only use one style. We typically only use hollow pipe transfer, right? All of our PVC, copper, black iron, whatever we're using for transferring water, it's going to be a hollow structure. So we have very little resistance on that. We do gain resistance if we start getting contaminations inside of our pipes. So if I have calcium building up inside of my water pipe, I'm going to reduce the flow through that water pipe, right? I'm going to change the resistance of that pipe. Well, when we're talking about electrons, electrons are going to flow based on the amount of electrons in the atom, how easy they are to transfer from one atom to the other. So different materials have different amounts of free electrons that we can move, because that's all we're doing. We're taking one electron and we're exciting electrons on other atoms, and we're just basically pushing them throughout our circuit. So depending on the amount of free electrons that we have on our material decides whether it is a good conductor of electricity or not. So if we look at those, you know, good conductors tend to be our aluminums, our silver, copper, titanium. If we look at glass, we're talking about now something that's going to be more of an insulative factor. If we talk about wood, it's going to be more of an insulative factor. But most material will still conduct electricity, will still flow electrons. Some just don't have as many available electrons in their atom. So some materials just are not excellent conductors of electrons. Insulators, we're going to talk about things like glass, wood, paper, mica, rubber, different plastics, and they have almost no free electrons. That means when we take our pump, we take our pressure, and we apply it onto that conductor, if it doesn't have very many electrons in its atom, it can't move those. So our electrons are not going to go anywhere. So that's what is going to be our insulators that we're going to have for our wires. And that's why we have different types of material as insulators for our conductors. If we look at electromagnetic windings, you know, we're going to use shellacs and lacquers, which fall into our glass, plastic, rubber material, that we're going to insulate that conductor, because we want to insulate our electrons. We want those electrons to flow through that conductor, and we don't want them escaping very easily. If we talk about very high voltage applications, sometimes we don't use any insulators at all. If we're talking about high voltage, high current lines on power transmission lines, we isolate those so far away from us because they do not have insulators on those. Those are live conductors where our electrons are flowing around that wire. And so
Can I ask a question?
Yeah, go ahead.
So the better the conductor, the easier the flow of electrons.
That's right.
So copper is a better conductor than aluminum. Silver is a better conductor than copper, and gold is the best conductor. So the insulating factor would have to be less, the less resistance, right? Because the less heat would be generated. Like going back to that resistor, the kW heater, the eye of the stove, it's just all the resistance is gathered right there, so you generate a lot of heat. So typically we use copper because it's cost effective, right?
That's right.
But initially we used aluminum, right? And we used to be, the rule of aluminum was it had to be like 60% larger than copper as far as being able to conduct the same amount of electrons.
Mm-hmm.
Yeah, just wonder, this for the guys that have run into the old aluminum wiring in their houses, usually the copper size can be much less than that. So it's cost effective. Copper's become the most commonly used conductor.
Absolutely. You know, and then we also get materials that are, they change their amount of electron flow based on the amount of pressure that's applied to them. So we're going to put them in a class of their own as semiconductors. So those are transistors and diodes, photocells. They are material that have both insulative and conductive capabilities to them, and they change based on the amount of pressure that's applied to those. So if they have very little pressure being applied to them, they could have very little conductive ability. And then as the pressure, the voltage increase, those materials actually change their molecular composition and allow those electrons to flow at different rates. So we have a variety of different semiconductors in our industry, and they all serve their own purposes. Some of them are more resistive, some of them are more conductive, but they change based on the amount of pressure that is applied onto those. All right, in an electrical circuit, of any type, we're going to have some type of a power source, whether it is generated or stored. We're going to have conductors, and we're going to have an electrical load. So if we look at just a very, very simple electrical circuit, if we take the one up on top, that's just showing where we're using a battery with a positive and negative side to it. So that is showing our flow of electrons. We're going to have a load, and then inside of our conductor, we're going to put a switch, which is just a broken conductor. Now, if we look at our series circuit, so we've been talking a little bit about parallel and series and how things are affected by the change of resistance. If I take a series circuit, so say I have, in this particular application, I'm going to use a 12-volt power source. So this is going to be a 12-volt battery, and I am going to use different resistive loads. So I'm going to put different light bulbs in that have different resistances to them. So the filaments, the actual elements inside of those, are going to have different resistive values to those. Well, if I look in a series circuit, and we were talking about how a resistor is going to affect the flow of electrons. Well, if I take that circuit and I have different resistive values, that means my electrons are going to flow through my conductors into my resistive side of my circuit, my loads. But because we have different loads, we're going to change the voltage drop across those. So if I take a simple series circuit, I apply 12 volts to it with a flow, remember my flow rate is going to be measured in amps, of 1 amp. Across that circuit, I have a different correlation of voltage drops across my loads based on its resistance. So if I take a 3 ohm bulb, a 4 ohm bulb, and a 5 ohm bulb, my voltage drop across each one of those, my total voltage drop on my entire circuit is 12 volts. But because I'm dropping my flow of electrons through each one, I have now a relationship of that voltage drop. So in a series circuit, I'm going to change my flow across each of those, because, let me grab my Sharpie, as I flow through my conductor, I'm going to pass through a resistor, right? I have a 3 ohm resistor. So it's a load, but that load is pulling a resistance on my total circuit. So I'm going to have a voltage drop across my load. So coming out of here, I'm not going to have a full 12 volts to supply my next bulb. I'm now going to have a 9 volt potential going into my next circuit. As I go into my next circuit, I'm now going to have a different resistive drop across that. I'm going to have a 4 ohm drop across my light bulb, right? So when I do that resistive drop across that, I'm using some of my potential energy. So by the time I come out of that load, I now really only have a 5 volt of potential to run through that circuit. So on a series circuit, we have to be very cautious of how we distribute our power, because if we're talking about this in a light bulb application, you know, the more bulbs that I add to my circuit, the less bright each one of those are going to be, because I'm going to evenly distribute my power across all of those, and I only have that potential for 1 amp for my entire circuit.
So this is how a dimmer switch works, or basically a rheostat. The motors we used to slow and speed up a resistor that actually lowered the voltage into the motor or the light bulb itself.
That is correct. We're just simply going to change the resistive load on our entire circuit. If we talk about a parallel circuit, so we're going to take that same applied pressure. So we're going to take our pump. In this particular application, we're using a 12-volt battery. That is going to be our pressure to supply for our entire system. Now, if we put it in a parallel circuit where we're actually evenly distributing our pressure to our entire system, and we're going to have different resistive loads on each one of those. So we're going to have a 3 ohm load or 3 ohm resistive load on our first bulb. We're going to have a 4 ohm resistive load on our second, and a 6 ohm resistive load on our third. Well, now we have all of our voltage being applied evenly to each one of those bulbs. So we have the available pressure for each one of them. So in a circuit, it depends on how I wire that as to how I'm utilizing my electrons. On a parallel circuit, I have 12 volts of pressure being applied to each one of these devices. Each one of these devices has a different resistive load to it, correct? Looking at those three bulbs in a parallel circuit, and we know that we have the available pressure to each one of them, but our resistance is different. On those three bulbs, are they all going to glow the same brightness, or are they going to be different?
I would say no, they're not going to glow the same, but I'm trying to figure out why now.
Because we
Like
have
a 100-watt bulb versus 75-watt bulb versus 50, 60-watt bulb.
that's all of our wattage is if we use that same Ohm's law and we plug in our voltage and our wattage changes, doesn't our resistance also correlatively change? So our wattage is a factor of voltage and amperage. So we can simply plug those numbers in and see what that resistive value change is. And absolutely. So we now have three different wattages of bulbs because our resistance is different on the three of those. So all three of these bulbs are going to have different brightnesses to them.
So they're going to consume electricity at different values as well, right? Because
Absolutely.
they're accepting more electrons.
We are
Just smarter
changing the way
bulb.
that we flow through our gates. Our resistor is just a gate for our electrons. If we do a joint combination of those and we use a parallel and series combination circuit, well, then we really are going to start adding some variations to it, because now we're going to be able to adapt the total applied voltage to individuals or as a combined circuit. And when we start talking about particularly things like Christmas lights, you know, if depending on the actual wiring of your Christmas lights, you can have a parallel circuit, a series circuit, or you can have a designed parallel series circuit. So if we take this exact same applied principle, so we have a 12-volt pump, so we have our 12 volts of pressure that's going to provide current flow for our entire circuit. If this, let me grab my Sharpie, if this one bulb on its own was tied into that original parallel circuit, it would have had 12 volts being available to it, right? Well, we don't have 12 volts available for this when we have a combination circuit, because what we have going on is we have a reduction. We're going to come out of our pump. We're going to have a change of resistance here. We're going to have a 2-volt drop across this first bulb. As we move into the second bulb, we're going to have a 4-volt drop across that. As we come out of that second bulb, we have lost 6 volts of our pressure across these two because we have flowed through them. We've passed through them together, not next to each other, but from one into the next. So our resistance adds as we pass through in our series circuit. So by the time we came out of this second bulb, we only had 6 volts of potential from this point to this point to be able to feed our bulb. So it changes how we have to look at the application of applied voltage depending on how our circuit is. And it gets a little confusing to understand that. And that's what we want to do, is just try to simplify the distribution of voltage based on its actual resistance. So voltage drop is an amount of electrical pressure. Remember, it is pressure, just like we're talking about with water pressure. It's an amount of electrical pressure that is applied to a load. Electrical load is a device that offers resistance of the current, and that most of them, they're going to perform some type of function or some type of work for us. Unintentional electrical loads, if we think about components of an electrical system, especially an HVAC system, that were designed to be conductors that change their resistance, and we actually do a flex train class on this where we go through measuring and evaluating changes of resistance across switches. If I take a conductor and I change its resistance, am I not also changing how the electrons flow through there? And I have the potential of converting my energy from electrical to heat energy. Well, if we look at particular an AC contactor. In that class, that's what I spent a lot of time focusing on, is an AC contactor. An AC contactor is a pair of contact points that is making our conductor, right? All it's doing is opening and closing our conductor. The flow, it is just a gate in our electrical system. Well, what happens if I build up resistance on my contact points? If I change my conductor to a load? That's
Well, you
all
create heat
I
and
generate
you
heat.
eliminate electron flow. So you might drop the voltage to a contactor to the compressor or the capacitor or whatever.
How many
That's the
times have
danger of
we?
letting the contactor get pitted.
Absolutely. And part of that class, and I encourage you guys to go back and look at our relays and contactors class that we have on the Johnstone Solutions University on YouTube, because we actually do. We burn out contact points on a contactor. A contactor was only good one time,
It's true.
the very first time it was energized. We arc across those contact points every single time that opens and closes. So we change the molecular surface of our contact points continually. And as we reduce the surface contact, we lose the ability to move our current through there properly, because those contact points were designed for a load to pass through, not to stop. And so as our contact points start burning and arcing across each other, we actually lose our surface contact to the point where we turn our contact points into now a resistor. And anytime that we have a resistive load, we are going to convert our electrical energy into heat energy. And that's why we burn up contact points on relays and contactors.
And to be honest with you, Clifton, it's kind of a compounding effect, because as you eliminate the electron flow, you increase the load. So the amperage starts going up on the back end, and you start pitting it even worse. So it compounds itself over time.
Well,
you should change contactors on your spring specials.
Contactors are a wear item. It's up to us to decipher how far into that circuit we actually are. And this is basically the same kind of a principle. If we look at measuring voltage drop across the circuit, we know that we have a voltage coming into a circuit, and we know that we have voltage on the outlet side on our load. If we change the resistance of our load, we can change the applied voltage across that. And we actually measure that out in the field when we're doing long applications of conductors. We measure voltage drops across those to see how much we lose. Because even if we think about a quality conductor, we think about copper as being a fantastic conductor of electricity. It is. It's not perfect. We actually lose voltage as we move across the conductor. If I take a number 10 wire and I run it 100 feet, I actually am having resistance across that conductor, right? It's not a perfect conductor. We're going to lose pressure. If I have a 1-inch water line with 60 PSI on it and I run it 100 feet, I'm probably not going to have 60 PSI by the time I get across 100 feet on that 1-inch line, because I am restricting some flow through that water pipe. It's the exact same philosophy when we're talking about electrical. We have a change in our voltage based on the resistance of our conductor, because we do not have 100% perfect conductors of electricity. We always have some type of resistance on those. So we actually take voltage drop to see how much voltage potential we've lost in our system. So that is simple circle. We can spend a lot of time on that one. I don't think we're going to today. Okay, so let's get into some of the effects of electromagnetism. Greg, is this anything you want to run with?
Well, I know that, when we do this class in Dayton, guys are unaware that magnetism is like the #1 function we use electricity for in the HVAC business anyway, actually in any business. So it's magnetism that drives a rotor inside of a stator, magnetism that pulls a contactor in. So they don't ever think about it like that. They think about something happening electrically, but they don't really think about the science behind it. So if you actually look at a contactor, the coil underneath there, when you put 24 volts to it or whatever the voltage is of that coil, it actually generates a magnetic field that pulls an armature down. So it's a mechanical thing happening because of the magnetism. And in the motor itself, if you ever look at a motor, you take them apart, I don't care if it's an ECM or a PFC or PSC, excuse me, the rotor that actually drives the blower wheel, it's not attached to anything really. It's basically sitting inside of a stator. Now the bearings keep it in place and keep it lubricated and all that stuff, but it's basically just chasing a magnetic current around the stator. And if you look at the windings on and I think we'll probably get into this in another class, the ECMs, how much more intense the windings are, how much better built the stator is. And all it is enhancing the magnetism of that system. And it's also enhancing the electrical current on it, or straightening it out, as it were, as you referenced earlier. So I don't know what the next slide is, but tired looking at the magnet. Trying to think of the new magnets they use, Clifton, on the ECMs are called
Neodymium.
yes, whatever he said. So it's like they become an enhanced magnet. And the funny thing is, when you're talking about enhancing the efficiency of a motor, they enhance the magnetic process of the motor, not just the electrical process of the motor. But I think sometimes we forget that that's what we're using electricity for. We covered the resistance part of it, the electric heater, the 5 kW heater, electric stove. That's a resistive type load instead of a magnetic type load.
All right, so if we talk about electromagnetism, if we're talking about the flow of electrons through a conductor, anytime that we flow electrons through a conductor, we're going to start generating a magnetic field. It's a byproduct of our functions. So magnetism is caused by passing an electrical current through a conductor. The magnetic field disappears when the current is turned off. It's a principle that we use for all of our electrical generation and all of our electrical transfer. So electromagnetic components depends on the core and the actual winding itself. Now, the strength of an electromagnetic field is going to be, of the magnets themselves, is going to be based on the number of turns in the winding. So, how much we have going through that. It's going to be based on the strength of our current. It's going to be based on our core material, the construction of it, and the length of our total coil. Back of the magnetomotive force, MMF, is the amount of energy used to generate a magnetic field. It's determined by the number of turns in the coil and the strength of current. So it's measured in amp turns. We'll talk about that here in just a second. So if we look at what's going on inside of a standard generator, so if we look at how we produce electrons and how we produce electricity, we're going to have a magnetic pole, we're going to have a stator, and inside of that stator, we're going to have some type of a rotor. And we're going to attach wire loop to that so that as we are moving, we're actually collecting electrons. So as we move that armature, our stator, rotor inside of that stator, we're actually interfering with that magnetic field, right? So we're going to capture some of those electrons as they're flowing. On a DC generator, it generates electricity in the same way as an AC generator. It's using a different rectification function of that. And we're going to use brushes on each side of our commutator. If we get into transformer basics, which is part of this class, I actually tend to break transformers down into an independent class on its own and go over the functionality of transformers. A lot of guys don't understand in voltage increasing and voltage decreasing, we're actually simply talking about how we flow electrons. So if we're looking at a transformer, and a transformer's purpose is to reduce the voltage, a lot of guys don't understand we're not making physical contact within that. All we are actually doing is we're taking electrons from one electromagnetic field, and we're using a secondary magnetic field to collect only a portion of those electrons. We are reducing voltage. So if we think about that, if we're just simply reducing the amount of pressure that can flow through a conductor, how we do that is relatively simple. If we look at a transformer, and this is just the standard step-down transformer, it's a function of electron flow. If I take we typically use iron core here for our transformers. If I take an iron core and I take a certain amount of windings and I wrap that around one side of my iron core. So this particular, on the left-hand side, we're going to bring 100 turns, so 100 wraps of our copper wire onto our iron core. And we're going to apply 120 volts of pressure onto it. We're going to put a 120 volt electrical circuit up against that iron core. Well, if I took on the right-hand side and I put 100 windings, I would have the same physical capability on either side. I would literally just transfer electrons from one field into the next field. Well, what happens when we change the amount of surface for those electrons to jump to? Because remember, all we're doing with electrons is flowing. We're using that iron core as a conductor of our electrons. We're simply moving those electrons from our magnetic field that has 100 windings over to our other magnetic field. Well, if we reduce the amount of surface that those electrons have to collect on, we're going to change the amount of electrons that can flow through it. We're just simply reducing the amount of electrons, which is consequently, remember, going to reduce our pressure.
I think that since we deal with transformers every day, I think it's something we should make sure they're clear on. So basically the winding differential is the voltage separation of the two. So if you have a 120 to 24 volt transformer, which is what we use most every day, you have a 5-to-1 ratio from the windings, right? You have 5 times less windings on the secondary side as you do the primary side. 240 volt transformer to 24 volts is 10-to-1. But there's other transformers we use in this industry, and it's called an ignition transformer, like on a oil burner, say, for those of us who still work on oil furnaces. It's just the opposite effect. You have a increase on the secondary windings versus the primary windings. So you take 120 volts and you make it 10,000 volts or 8,000, whatever it is. And that's an 83-to-1 winding ratio. And I think the important thing is what a lot of guys don't understand, and Clifton built this incredible trainer, the mad scientist, on a air conditioning pad like he tends to do. And it shows that they truly never come in physical contact with each other. The primary winding versus the secondary winding. There's actually the iron plates in the middle of it that create a shared inductance so that the secondary winding is able to grab the amount of electrons in ratio to the primary windings.
Absolutely. Absolutely.
You get that, Jesse?
So like in this particular example, if we have 100 windings coming in, we don't have a shared electron flow. We don't have 100 windings coming out. If we reduce our windings down to 50, we now only have half of the potential surface for our electrons to collect on, right? Because we're collecting the same amount of space on that iron core. We just now only have half as much space for our electrons to jump onto. So that's all we're going to be able to do. We're going to be able to collect half of the electrons that we had as a potential supply on our incoming side of our transformer. So we reduce our windings down to 50. We can now only collect 50% of our electrons, half of our electrons. So our pressure is going to be reduced because we do not have the potential for our pressure to build to 100%. So if we have 100 turns on our primary side, 50 turns on our secondary side, we apply 120 volts onto our primary side, we're only going to be able to collect half of them coming out, and we would only have a 60 volt outlet pressure on that transformer.
May I ask a question?
Yeah, absolutely, Angel.
Why some of the transformers are noisy, make noise, some not at all?
Where's the noise coming from?
Probably the magnetic or the plates inside of it.
It's our magnetic field. You are actually listening to the flow of electrons through those plates.
But I have, two different transformers. One brand, for example, Honeywell, their transformers are not noisy at all.
That's right.
Other brands are noisy.
You betcha.
Yes.
It's true.
One of the things that I always discuss in all of our classes, especially on our Thursday Flex Train classes, as technicians, we need to be able to understand the products that we're working with. From a construction point, if we take a component, we have 2 or 3 different manufacturers of that component. There's really not a lot to it. When we dissect, if we're looking at a transformer right here, and in our transformer class, we may end up doing that as one of our classes here. If we look at a transformer, we literally have an iron core with 2 magnetic windings, 2 magnetic fields. That is it. There's nothing to it. It all comes down to manufacturing. If we take a product that is poorly manufactured, we're going to have poor results, right? So we take companies like Honeywell, who put millions of dollars into research and development to manufacture a product that is well constructed, you probably are going to have a quieter transformer than company B or company C that does less quality control on their products. I did a capacitor class here just a couple months ago, and we took like the Turbo 200 capacitor, and we talk about it from a manufacturing standpoint. A capacitor is a film, hundreds and thousands, sometimes thousands of feet of film that is rolled into a very, very tight spiral, put inside of a shell with a dielectric fluid, and we store electrons on those plates. It's very simple. We actually cut one open with a can opener and look inside of it. If we look at those capacitors, there's a lot of manufacturers that build replacement capacitors. And I actually had a guy send some emails about a company that from another country, an imported capacitor that was constructed exactly like the Radco Turbo 200 capacitors. And out of his first 5, 3 of them failed within the first month. I don't know that I've ever had a Turbo 200 fail in the field. It all comes down to quality of manufacturing. So yeah, you buy an inexpensive transformer that doesn't have quality construction of its plates. Just think about those plates. So if you look at the plates on that iron core of a transformer, we have a lot of plates that are stacked together and riveted together, right?
Mm-hmm.
As those electrons are flowing through there, we're disturbing the entire surface of that material. Those electrons are moving through it. It's moving electrons of its actual component part. We're going to have some vibration. We're going to have some frequencies moving through those. If those plates are not tightly compacted and not made of consistent material, we can have vibrations within those plates. And we're going to generate frequencies. So it very much comes down to construction and the amount of load, because if we're trying to pull more electrons off from that transformer than what it is capable of, we're also going to start generating some heat and some additional noise to our components. So it's in construction very much. But yes, in a transformer, you are hearing a flow of electrons from different magnetic fields. Now, on that same principle of looking at a transformer and how electrons flow in a circuit, if we change the potential collection of electrons, can we affect it in an opposing situation? If I take that same 120 volts and I apply it onto 50 turns on this particular application, so I have a potential amount of electrons that can jump essentially from my magnetic field onto my iron core. What if I take, and on the secondary side, I double the amount of space that my electrons can collect onto? Because my electrons are flowing extremely fast. I can actually show you the formula how fast they're flowing. Very, very, very quickly. I have the potential to collect more electrons than what I had generated. If I have a 4-inch pole and I apply electrons onto that, but it was actually an 8-inch pole, I put a conductor here and a conductor up here. This 8 inches of pole can be completely full of electrons. Just because I'm only applying it to half of it doesn't mean that the entire pole is not full of electrons. We are absolutely filling it full of electrons. So if I apply 120 volts of electrons onto a surface and I have the ability to collect twice as many of those electrons by putting 100 turns, doubling my potential magnetic field, I can actually collect more electrons than what I was generating. My pressure can increase. What does it do to my current? Now, if we go back to our Ohm's law, we can simply plug those numbers back in. If I'm increasing my voltage, what's going to happen to my current? Drops. It's going to nosedive. Yeah, proportionally. So I can increase my pressure. That's what a step-up transformer does. I've had a lot of guys ask me, man, how do we increase pressure? How do we increase voltage on a circuit? How does a step-up transformer work? It's simple. We collect more electrons than what we're applying because our electrons are flowing faster than 60 cycles per second. So we have the potential to collect a lot more electrons than what we're producing. We just aren't going to be able to move them as fast. If we were talking about water, if I have water coming in on a pipe at 60 psi and I run it through a pump and I boost it up to 120 psi, I don't have the same gallon per hour, do I? Because I've had to run my pump to increase my pressure. It's correlative in electrical electron flow. When I increase my pressure, I'm reducing how fast I can flow that. So when I increase my pressure, I reduce my potential current. I reduce how many amps I can flow through that circuit. I still can get my voltage up. I just don't have as much work that I can do with it.
That's key. I
Yeah.
guess knowing that a standard 24-volt transformer on a furnace can only do 1.66 amps of work, I believe. You know, we get that argument that everybody says a 3-amp fuse is too small to put on a circuit board. Hell no, it's not. It's almost twice the size you need. But conversely, if I may, looking at this diagram here where you stepped up or you gathered more electrons than you actually sent to the actual or the core, you don't gain potential though, because if on the secondary side of a, say, an ignition transformer in an oil furnace is 10,000 volts. It's not like 10,000 volts that'll light up a city. There's
Right.
still limited potential there. So it's like a bug zapper. You know what I mean? It's killing those damn flies out there, but it's not going to kill you. It doesn't feel good, but there's not that potential there. It did increase the voltage, but the potential's not there.
Absolutely. So we can increase our voltage, but we're going to reduce our potential current that we can supply to that appliance. So a very different perspective on looking at a transformer. And that's what we do in our FlexTrain classes. We take things that we work with on a daily basis and we just explain them, how simple they really are and why they fail. If we think about a transformer is going to fail. And I encourage you guys as technicians to try this. If I have a transformer fail, remember, I have two separate windings there. Find out which winding failed. Because I will guarantee you, if you have a transformer that burns up, it burnt up because we had too much load. We tried pulling too much load on one winding or the other, right? It's typically our secondary winding. So the next time you have the opportunity to find a transformer that is burnt up in the field, take that transformer, get your meter, put it on resistance, and take a look at your two windings. We actually do that in my transformer class. We take a burnt transformer and we figure out which one of our windings failed, because typically you're only going to burn up one of them and the other is still going to be intact. And that is a good way for you to understand exactly what we're showing you here. You have two completely separate magnetic fields on a transformer. They're very isolated. If you take the wrap off from the side of a transformer, you can see both of those windings. They're insulated by a plastic plate. I don't think I have that in this one. I know I've got some slides that shows that. So we can actually look at those windings independently on a transformer, and I encourage you guys to do that. So saying that, we can actually decipher the number of turns of wire on a transformer based on its proportion of voltage. So if I had any three of these numbers, I can tell you what the fourth one is. So if I had a primary voltage and I had a secondary voltage on a transformer, so I've got 120 volt in and I got 24 out. If I know the number of turns on one of those windings, I absolutely know what the correlative number is on that other side. So it's simply a relationship of number of windings that is going to give our relationship of voltage between those transformers. So in the commercial industrial side, if I have a transformer that is completely roasted and I don't know what the original voltage drop across that transformer was, I can literally count the amount of windings on a thing. It's a lot of time, it's a lot of individual windings, but you can absolutely do that.